Hello students, in the last video we had discussed the points with respect to electrostatics, that is electric charges, Coulomb's law, basic properties of electric charges, relative permittivity or dielectric constant, and definition of 1 coulomb. So today we are discussing the rest of the part of this chapter in the section revision 2 of the chapter electrostatics. So the next point is principle of superposition. So what is the principle of superposition? We know that the statement is when a number of charges are interacting, the resultant force on a particular charge is given by the vector sum of the forces exerted by individual charges. That means how to explain the term principle of superposition. So suppose if you consider, look at here, suppose if you consider this is charge Q, and at the point charge Q there are number of charges are interacting. That means suppose here if you represent charge Q1, here suppose you represent charge Q2, here you represent charge Q3, suppose this one is charge Q4, this is your charge Q5. Then the statement is represent the sum of individual charges exerted by the force. We know that when we consider charge Q1 on the right hand side, then the force exerted on Q1 on left hand side. Suppose this is Q2, the left hand side we are consider here, that is F2, here is F1. Same for Q2, we are consider opposite charge, that is F3. These are called equal because in Coulomb's law, when we consider in terms of vector form, the Coulomb's law is represent F21 is equal to minus F12. That means the directions, direction of the forces are opposite, but the magnitude of the charges are equal. So whenever we consider term superposition and when we consider the number of charges are interacting from the single charge, then the forces are exerted by individual charge. We have to take sum of all the forces, but the direction of charge and the direction of force both are in opposite direction. That's why we have considered the sign, that is negative sign. So suppose if you consider number of charges and if we apply the Coulomb's law on each charge, then in terms of charge Q1 the term F1 is represented. See, first we know that F is equal to 1 upon 4 pi epsilon naught Q1 Q2 upon R square. This is our definition of Coulomb's law when we consider in terms of two charges. So here we are starting from suppose charge Q1. So in terms of charge Q1 exerted on another charge, that is Q2, then we can consider F1 2 is equal to, because we are consider pair of the charges, so 1 upon 4 pi epsilon naught again Q1 Q2 upon R square. Suppose if you consider the another charge, that is F12, next one suppose if we consider F13, that is third charge with respect to first one F13, then we can write 1 upon 4 pi epsilon naught Q1 Q3 upon R square. In case of n number of charges, we represent F1n, which is equal to, we can say vector form, 1 upon 4 pi epsilon naught Q1 Qn upon R square. And suppose if you are taking sum of all the charges, then sum of all the forces, then we'll get resultant force exert on charge, that is Q. So we can write F is equal to F12 plus F13 plus F14 in case of plus F1n. Okay, so 1 upon 4 pi epsilon naught is common, taking outside, so we can write 1 upon 4 pi epsilon naught in bracket, write down Q1 Q2 upon R square plus Q1 Q3 upon R square up to Q1 Qn upon R square. Instead of this one, this series we are representing in terms of summation of all the charges, then we can write 1 upon 4 pi epsilon naught summation I, that is starting from 1, that is charge Q1 up to n number of charges. So we can write I starting from 1 up to n Qn, we represent Qn, and here we can write Q0 into Qn upon R square. This is called resultant force exert on charge Q, and that charge we represent in terms of principle of superposition. Okay, so this equation gives the resultant force exerted on a particular charge, that is charge is denoted by small q. The next point is electric field. So what is the electric field? The simple definition of electric field is force per unit charge. That means whatever force exert on this charge, if you are taking the ratio of charge with this force exert on that charge with respect to given charge, will get electric field exert on that particular charge. So we can write E is equal to force per unit charge, F upon Q. And if you have to find out dimension of E, which is given by L1 m1 t raised to minus 3 and I raised to minus 1. Then how to define the derivation to find out electric field at a particular point? So consider two charges Q and capital Q and small q be the two charges separated by distance r. Look at here. Suppose if you consider here is one of the charge capital Q and here another charge is small q, and the distance between these two charges we are represent in terms of r. So therefore by using Coulomb's law we can write F is equal to 1 upon 4 pi epsilon naught. Here we represent Q and another one we represent capital Q upon distance square r square. The force exerted on this charge is force exerted on both charges were present in terms of this one using the definition of electric field intensity. Therefore E is equal to F upon Q. So use this force, so we can write 1 upon 4 pi epsilon naught Q upon r square divided by Q. So this Q and this Q get cancelled. The final answer is E is equal to 1 upon 4 pi epsilon naught Q upon r square. This is called electric field intensity due to a charge capital Q. So in this equation or in this expression we have considered different cases. That means that epsilon, this equation is represent when the medium is rarer or medium is vacuum. Suppose if we consider in case of medium, material medium is given, then we can write the first case is, I am writing over here, the first case is if epsilon 0 is equal to epsilon. That means if we consider a material medium, then only thing is that we can write E is equal to 1 upon 4 pi. Instead of epsilon naught we can write epsilon only Q upon r square. So in case instead of epsilon we are using the definition of dielectric constant. We know that dielectric constant or relative permeability ER is equal to epsilon upon epsilon naught, or we can write K is equal to epsilon upon epsilon naught. Therefore epsilon is equal to epsilon 0 K. Put this value over here, so we can write E is equal to 1 upon 4 pi epsilon naught K Q upon r square. So this is called second equation when we can consider the material medium is when we consider a material medium. This equation is related when we consider a medium is vacuum, and instead and the third case, second case, if we say that medium is rarer, so the value of K is 1, and again E is given by 1 upon 4 pi epsilon naught Q upon r square, same as the previous equation. So these are the different cases of electric field intensity. The next case is, suppose the next case we are represent in terms of electric field, or we can say that the second definition of the electric field in case of potential difference and the distance between the two charged plate is given by E is equal to V upon D. This is your first definition of electric field, and second definition is E is equal to V upon D. So that V is called potential difference and that D is called difference between two charged plate or two parallel plate having positive and negative charges. Okay, so suppose look at here, if we consider this is one of the plate having positive charge and this is another plate having negative charge, the distance between this positive and negative we are represent in terms of capital V. And suppose if we say that Q plus Q charge is present in between these two plates, so when that plus Q charge is moving in a right direction, then this point Q charge and this plate we are represent the separation between two plates. And suppose if we say that this plus Q charge is exerted on the left hand side, then the distance between this charge and that plate we are representing in terms of d, and we can say that E is equal to V upon D. This equation shows the practical way of the electric field. This equation shows a theoretical proof of the electric field, and this is called practical way of the electric field. So there are two types of electric field. First one is uniform electric field. What is uniform electric field? The definition is a uniform electric field is a field whose magnitude and direction is same at all points. So first type, we can say that first is uniform electric field. That means suppose if you have considered positive plate and negative plate and all the charges distributed from positive to negative in a parallel direction, then we can consider uniform electric field whose magnitude and direction is same at all the points. And second type is non-uniform electric field. In that the magnitude of the charges is same but direction is not same at all the points. That means we can say that a non-uniform field is a field whose magnitude and direction is not same at all the points. In this case, magnitude of field is same but direction of field is not same. That means we have considered this type of diagram. Look at here. Suppose this is central part and the direction of this charge is represented in all over direction. So we can say that the directions of this charge Q are different, not same, but the magnitude of the charge Q is same at all the points. So this type of field we are represent non-uniform electric field. This type of field we can say that uniform electric field. The next point is, what are the characteristics of the electric lines of forces? So the first characteristic is, I am writing the back page. The next point is characteristics. Next point is characteristics of electric lines of force. So first characteristic is the electric lines of forces originate from positively charged object and end on negatively charged object. That means suppose if you have considered one of the rod having two terminals, to get suppose this is negative terminal and this is positive terminal. So always so remember that the electric lines of forces originate from positive and end up to negative. Originate from positive and end up to negative. This is called first characteristic. Second is neither intersect nor meet each other. That means these electric lines of forces are parallel to each other. They never intersect or nor meet at a particular point. The third point is the lines of forces leave a conductor normally. That means when this positive and negative charge is passing through this conductor, not inside the conductor, but if you consider solenoid type conductor, so if that positive and negative charge is passing through this conductor, then after passing they leave conductor normally. That means the shape and size of that conductor does not change anywhere. It is same at all the points. The fourth characteristics is the electric lines of forces do not pass through conductor. That means this plus charge did not passing through inside of the conductor, or this negative charge did not passing through the inside of the conductor. Because of that one, electric field is equal to 0 inside of the given conductor. The fifth characteristics is the electric lines of forces is, the electric field intensity. The term intensity is called strength of the electric field. Whenever we are consider term electric field intensity, it represents the strength of that electric field. Remember this. So the electric field intensity is directly proportional to the number of lines of force per unit area. That means suppose again if you consider one of the conductor, and whatever positive and negative charges is passing through this conductor within the area, suppose number of lines are number of charges are passing through this small surface area, then we can say that electric field intensity is maximum. Suppose less number of charges or less number of electric lines of forces passing through the wide area or wide range area, then we can say that the electric field intensity is minimum. That means what? The intensity of electric field is directly proportional to the number of lines per unit given area. The next point is where electric field is large, lines are crowded, and electric field is small, then the lines are separated from each other. That means what? Suppose is in this terminal, positive terminal, suppose electric field is large, then these lines are crowded in this region, and suppose in negative charges electric lines are less or small, then the lines are separated from each other, or they are widely separated from each other. And the last one is these electric lines of forces are parallel and equally spaced at every point. They neither intersect and nor meet each other. These are the very important characteristics of electric lines of forces. We have to use these characteristics in this chapter at every step. Okay. The next definition is electric flux. What is the term flux is defined? The electric flux is usually defined how many number of lines of forces are passing through given area. That means suppose this type of area is given and number of lines are passing through this area, and total area is represented by S, and suppose there are number of lines, n number of lines are passing through this given area, it defines the term electric flux, and that symbol is phi, and that phi we can write E into S. E is called electric field within the area and S is called total surface area. If you consider small surface area, that means this total surface area, suppose if we consider only that much area, the total is S, and small area we are represent in terms of ds, and if electric lines of forces passing through the given area. So apart from this, how many lines are passing through this small surface area, that defines the term d phi. That is called small electric flux or electric flux within the given area or small surface area, which is again nothing but E into ds. So these are nothing but the term electric flux is defined, that is d phi is equal to E into ds. Okay. And if we consider total surface area, then electric flux is nothing but E into S, and depending on the electric flux, Gauss law is defined. Gauss law is described. So what is the Gauss law? Gauss law is, the statement is, the flux of the net electric field through a closed surface equals to the net charge enclosed by the surface divided by epsilon naught. That means whatever value we are given in terms of small surface area, that is E into ds or total flux phi, so that phi is equal to Q upon epsilon 0. Suppose if you are consider this is closed surface area and there are number of charges which are present in this closed surface area. So if you are taking the average of this closed surface area with respect to permittivity of that medium, and if you are taking the ratio of both, will get total electric flux enclosed by the given area, and that is nothing but Gauss law, that is E into ds is equal to, we can write Q upon epsilon naught, and we are considering integration, and if you are taking integration of E into ds is nothing but total flux, which is equal to Q upon epsilon naught. This is the very important theorem in electrostatics. In this chapter, that means in 12th standard, we will discuss the applications of Gauss theorem. Because of that one, first you have to understand what is the statement, what is the actual definition or actual statement of the Gauss law. In the next video, we will discuss about the 3-4 topics, that is electric dipole and the continuous charge distribution. We will see in the next video. See, if you have any difficulties regarding any topic, any single topic, you can ask, but you have to write down all the notes in your notebook. We will see in the next video. Thank you.